My name is Kylie McCook, and this is my Physics 1 Lab 1 presentation. So for our introduction, the purpose of this lab was to demonstrate Newton's second law of motion in an actual example. The lab allowed us to compare the computational position time graph to one that was made with data that was manually collected, which obviously left room for errors in our own documentation of the data. So Newton's second law describes the acceleration of an object depending on the net force applied to the object and the mass. So in this lab, the net force acting on the system was 0, so the velocity of the object was constant with no change in momentum in theory. And below I have the formulas all listed for net force and change in momentum, which is also net force. So you can see I started off with F net equals the change in momentum over the change in time. And then you see as we work down in the formulas, we eventually also get the velocity update formula as well as the position update formula. And to set up the experiment, I first started by recording a video of a marker rolling on the table in a straight line at constant velocity. I then uploaded the video into Tracker to gain coordinate points of the marker at specific time intervals. For the point of my experiment, I used 0.107 as my delta t. And then I used the starter code that was listed in Canvas to create the computational model of my own experiment using the data collected. I created a position versus time graph, overlaying the computational model and my actual model in Excel, and I compared the two for accuracy. So here I have pictures. The first one on the left shows the system versus the surroundings. In this case, the system is the marker and the surroundings is the air in the table. And then on the right, I have my tracker video with the origin defined, and then from there, I let the video play, and I took coordinate points from each time interval. And here you can see the video. Okay, and then the setup of the code, I began with the starter code, then I changed it to fit the data collected. I changed the object's mass and initial velocity. I also adjusted the time and delta t as variables and for the while loop. And I updated the formula for object velocity and position in the while loop since there was assumed to be no friction or net force on the object. And then here's the glow script code that I used. You can see down here for the ball velocity that I just set it equal to velocity, and then for position I set it equal to the position plus the ball velocity times delta t, since there was no force acting on the object. And then these are the models that I got. As you can see, the position changed in a linear pattern and the velocity remained constant throughout the entire thing. This is the graph that I created in Excel. This was the model in the red line, and then the blue line shows from the data that I collected using Tracker. So as you can see, the blue line does veer off from the red line just due to the fact that we cannot account for no friction or air resistance, or maybe my push had it going in a slight angle instead of going perfectly straight. And here I listed those errors again. As I said, the table is also kind of slanted, so it made the marker roll at an angle, which also affected its position graph. We also have possible errors with Tracker. The placement on the object might not have been in the exact same position for every time interval, so I may not have had it directly in the middle or directly on the bottom of the marker like I had at the origin. And then further questions was how would flipping the axis change the results? In my case, I had negative x values, so if I were to switch them to positive, it would just reflect the graph over the x-axis. Everything else would stay the same, the values would stay the same, other than the fact they'd just be positive instead of negative. And is it possible for you to say how many pushes and pulls were added together to give 0 net force in the case that I observed? So in the data that I collected, since the position and time graph is not exactly linear, we do know that there were forces acting on the object that did not produce a net force of 0. Those forces could have included my push, as well as friction, air resistance, and slanting. And that's it.